Hello everybody, welcome to video number 13. This video is going to be on pH and how to calculate pH. So we're going to start with just a quick question that I want you to think about. And I want you to think about what is pH and where have you heard this term before. So you've probably heard it before, maybe if you're testing your fish tank water, or you're testing a pool or hot tub water, okay? Or maybe you've studied it a little bit in middle school, okay? You should have been introduced to this concept. Today I want us to be able to calculate it. So to introduce this concept, the pH scale is a scale that goes from 0 to 14 describing the how acidic or basic something is. And it's very important because the pH has a relationship with how healthy that environment can be. For instance, if we're dealing with a fish tank, or if you're dealing with an ocean or a body of water, okay, or rain, okay, this pH level helps us understand how healthy that environment is, okay? And it has been understood that the pH of the ocean is becoming more acidic, and this is having a negative impact on the animals that live in it, in the environment, okay? The coral reefs, or the fish and the plants, all those things that live in the ocean, this is having an impact on that. So if we study and understand how pH is changing, okay, maybe we can think of ideas on how to help it and get it back to a healthy environment, okay? All right, so the pH scale, like I said, is a number scale going from 0 to 14 describing the concentration of hydronium ions. Now, I know you're not familiar with what an hydronium ion is, but what we can say, or what is a hydronium ion, is hydronium is an H3O+, okay, directly related to H+, okay? So this is a hydronium ion. You could also say H+, okay, is the same thing. Why? Because when I have H+ in water, it attaches itself to H2O and creates hydronium. Okay, when I have H+ in water, it attaches itself to H2O and creates this H3O. So the pH is a measurement in how much H3O or H+ there are in a solution. They're the same thing. They go hand in hand. Okay? And this is in this number scale helps us simplify this concentration. Okay, so in order to simplify this concentration, we're going to do a small calculation to get this whole number. Yes, it can have a decimal, but typically we can simplify it and just call it closest to the whole number to really understand how acidic or basic this substance is. Okay, and here we see how acidic or basic common things that we deal with are. Okay, water, again, 7, milk, human saliva, blood should be somewhere around 7. Okay, stomach acid, very strong, low pH of -1. A very strong base is things like bleach, a very high pH, very basic. Okay, so if I look, these bases tend to be things like cleaning or soap substances, and down here acids, you see things like orange juice, sodas, vinegar, things like that. Okay, commonly I would say more juices that we ingest, okay, or fruits. Okay, so a solution is acidic if the pH is less than 7. A solution is basic if the pH is greater than 7. And I've seen this as an ACT question, so make sure you leave here remembering that. A neutral solution is 7, right in the middle. So what does this mean for the concentration of each of these things? Remember, both of these together make water. Well, what we're calculating and what we're doing today is determining the pH based on these two concentrations. So if I look at a table, I should be able to see some patterns, okay? pH is 3, that means the pOH is 11, okay? Notice the hydrogen ion concentration is 1 times 10 to the -3rd. The hydroxide ion is 1 times 10 to the -11th. So looking at kind of common patterns in this table, I should see these exponents are close to the pH level. Okay, the exponent of this value is close to the pOH level. So it looks like the exponent of the hydrogen ion concentration is close to the pH level, and the exponent of the hydroxide ion concentration is close to the pOH level. How are these two related? 3 and 11, 9 and 5. You might not notice this right away, but what do all of these add up to? 9 plus 11, 14. Or excuse me, 3 plus 11, 14. 9 plus 5, 14. 7 plus 7, 14. 0 plus 14, 14. 12 plus 2, 14. So there's going to be some common patterns that you're going to see, and you're going to see a strong relationship between H plus, OH minus, pH, and POH. And that's what I want us to understand today. So like I said, pH is a measure of the acidity of a water solution. It is defined as the negative log of the hydrogen ion concentration, and these square brackets mean molarity. So this is concentration in molarity, okay? And that's why we've been studying molarity. So on your calculator, you can find that log button. And if I take the negative log of the hydrogen ion concentration, you get the pH, okay? So what is a log? Hopefully you've studied that a little bit. I'm going to review it, a basic definition, okay? All we really need to know is where the button is. But a log is simply kind of taking the inverse of an exponent of something. For example, log base 10, we're going to use base 10. Log base 10 of a million is what? Okay, what is that asking? That's saying 10 to what power equals a million? We're taking the inverse of the exponent. Okay, so 10 to the 10th, or excuse me, 10 to the 6th power is a million. So the answer to this question is log of a million is 6, because 10 to the 6th power is a million. And that's what we're doing here, okay? We're using this log function to calculate the pH. Why did they choose this? I'm sure because it's a lot easier to say the pH is 7 than to say the hydrogen ion concentration is 1 times 10 to the negative 6th. All right, so if I have a solution where the hydrogen ion concentration is 1 times 10 to the negative 6th, what is the pH? Well, I'm going to take the negative log of 1 times 10 to the negative 6th. That's 6. So what is the pH? 6. Okay? Now, working backwards, if I'm given the pH and I want to get the hydrogen ion concentration, I'm going to use this up here. But we'll get to that in just a minute. What if your solution has a hydrogen ion concentration of 3.23 times 10 to the negative 11th? Well, like I said, this exponent does have something to do with it. And it is easy to look at that exponent if your coefficient is 1. But if your coefficient is not 1, it's best to put it in your calculator. Really, I want you guys putting it in your calculator all the time. So here I take the negative log of this hydrogen ion concentration, the negative log of 3.23 times 10 to the negative 11th, and it's going to be somewhere around 11, but it ends up being 10.5. So the pH of this solution is 10.5. Okay? All right. Okay, so what if your solution has a pH of 5.4? What would the hydrogen ion concentration be? This is, like I said earlier, we're working backwards. So here we're going to use this calculation. And you are given this equation, if you want to call it that, on your worksheet 9.3. So here I'm going to take 10 to the negative pH, and that's going to give me my hydrogen ion concentration in molarity. So 10 to the negative 5.4, I'm going to use that triangle, or that kind of upper, I'd say it's kind of an arrow pointing up. 10 to the negative power of 5.4 is 10 to the power of negative 5.4 is 3.98 times 10 to the negative 6. That means my hydrogen ion concentration in a solution that has a pH of 5.4 is 3.98 times 10 to the negative 6. But what about POH? Well, remember, pH and POH are related to each other. It seemed to me a second ago we said pH plus POH always equals 14. And this, and again, they have that direct relationship, or I should say an inverse relationship, because as one goes up, the other goes down. They're always going to add up to 14. And this brings us back to water. Okay, so as I increase the hydrogen ion concentration, the hydroxide ion concentration is going to decrease. They have that inverse relationship. So if we add a base, we increase hydroxide, that means the hydronium ion concentration, the H+, is going to decrease. They have an inverse relationship. So POH is less commonly used in society, but it is used a lot in chemistry. pOH is just the negative log of the hydroxide ion concentration. In water, the pH is 7, so the pH, or the hydrogen ion concentration, is 1 times 10 to the negative 7th. If I take the negative log of that, I get 7. The hydroxide ion concentration is also 1 times 10 to the negative 7th. I take the negative log of that, and I also get 7. So together, they're always going to equal 14. So if pH is 6, what is pOH? Hopefully, you understand. 6 plus what equals 14? 8. The pOH is 8. And I want us to know and understand that relationship very well, and that's what our homework is. This is a chart used to go from pH to hydrogen ion concentration to OH to pOH and how they're all related. So this can maybe help you convert between them, okay? So let's do some quick practice before we get into some worksheet problems. The pH of a solution is 8.2. Therefore, the hydrogen ion concentration is what? So I'm going from pH to hydrogen ion concentration. It looks like I'm going to take 10 to the negative power of the pH to get the hydrogen ion concentration. 10 to the power of negative 8.2 is 6.31 times 10 to the negative 9th. Okay? The hydrogen ion concentration, here I'm starting at hydrogen ion concentration. Is it acidic, basic, or neutral? So I'm probably going to want to identify the pH, and then I can easily identify is it acidic, basic, or neutral. So I'm going to take the negative log of that hydrogen ion concentration and get 12. The pH is 12, that means it's basic. The pH of an acidic solution is 4, the pOH is what? Again, remember both of them add up to 14, so the pOH must be 10. Okay? All right, if the pH is 2, what is the OH concentration? Well, remember, if the pH is 2, the pOH must be 12. And then I can go from pOH to hydroxide ion concentration by taking 10 to the negative, or excuse me, by taking, 10 to the negative power of 12, and that gives me 1 times 10 to the negative 12. The hydrogen ion concentration of a solution is 3.23 times 10 to the negative third. What is the pH? I'm trying to figure out pH. I'm starting at hydrogen. I'm going to take the negative log of the hydrogen ion concentration, and that's going to give me pH. So the negative log of 3.2 times 10 to the negative third is 2.49. All right. The pH is 4.5. What is the hydrogen ion concentration? Again, I'm going between pH and hydrogen ion concentration. I'm taking 10 to the negative power of the pH. 10 to the negative 5.4 is 3.16 times 10 to the negative fifth. There's my hydrogen ion concentration in molarity. All right, let's do a few problems from the back of your worksheet, worksheet 9.3. Number 4. The hydrogen ion concentration is 1 times 10 to the negative 7th. If I take the negative log of that, I get the pH of 7. 7 plus what equals 14? 7. Is this acidic, basic, or neutral? Hopefully you say neutral. All right. Letter B, the hydrogen ion concentration is 1 times 10 to the negative third. If I take the negative log of that to get the pH, I get 3. The pOH would then be 11. Is that acidic, basic, or neutral? Again, I look at the pH. If it's less than 7, it is acidic. The hydroxide ion concentration, letter F, is 1 times 10 to the negative 7th. If I take the negative log of that, I get the pOH. So that gives me a pOH of 7, making my pH 7. Looking at the pH of 7, is it acidic, basic, or neutral? Hopefully you say neutral. Letter G, the hydroxide ion concentration is 8.3 times 10 to the negative 10th. If I take the negative log of that, I get the pOH of 9.08. Okay? The pH would then be, I would take 14 minus 9.08, and I get 4.92. The pH is less than 7, making the solution acidic. Okay, hopefully you can finish doing that chart and the problems above it. Problem number 5, a little less, I should say straightforward, but, okay, hopefully a couple problems gives you a basic explanation. HCl is an acid, okay? You're going to focus on the H or the OH, okay? So the Cl in this case doesn't matter. So the concentration of this is a strong acid. It dissociates completely. The concentration of this 0.01 molarity HCl, the concentration of H is 0.01. So if I take the negative log of 0.01, I get a pH of 2. So a pH of 0.01 molarity HCl is 2. If I look at part C, it looks like OH is what's going to matter. The Na doesn't matter. Okay, so if I take the negative log of this, that's going to be my POH, because that's my hydroxide ion concentration. So that gives me a pH of 2. My pH would then be 12. Okay, so when I say complete ionization, dissociation, that's saying strong acids completely dissociate it, meaning the concentration here is also the concentration of the H or the OH, whatever you're looking at. Okay? All right, so there's some examples and a basic definition of an acid, base, pH, and POH. So hopefully you understand the basics of acids, bases, what pH means, and how to determine if a substance is an acid or a base. Your homework is to finish worksheet 9.3, acid-base conjugate pair identification on the front, and pH worksheet on the back. Good luck, and please let me know if you have any questions. I'll see you soon.